In this video, we are going to use prime factorization as a tool. Instead of seeing prime factorization as an endpoint, we will use it to answer bigger questions. Like, what are all of the factorizations of a number? What do the divisors of a number have in common? How can we test divisibility? How can we find factor pairs efficiently? Let's start with a small number, 12. What are all of the factorizations of 12 into positive integer pairs? Well, we can do 1 times 12. We can do 2 times 6. And we can do 3 times 4. These are all of our factor pairs of 12. So 1 is a special number, but 12 has a prime factorization, in particular 2 times 2 times 3. 2 is prime, but 6 is not. That's 2 times 3. 3 is prime, but 4 is not. That's 2 times 2. So with each of these products, I have 1 2, I have a second 2, and I have a 3. So no matter how I break them down, I still have 2 2s and 1 3. Now, let's find all the factorizations of 60. We can have 1 times 60, 2 times 30, 3 times 20, 4 times 15, 5 times 12, and 6 times 10. Now, let's find the prime factorization of 60. 60, I'm going to go ahead and break up into 6 and 10. 6 is 2 times 3, and 10 is 2 times 5. So we have 2 times 2 times 3 times 5, or 2 squared times 3 times 5. Now, let's think about the prime factorizations of each of the divisors. 1 was our divisor, that's just 1. 2 was another one, as well as 3. These are prime numbers. 4 is 2 times 2. 5 is 3 times 5. 6 is 2 times 3. 10 is 2 times 5. 12 is 2 times 2 times 5, or 2 times 2 times 3. 15 is 3 times 5. 20 is 2 times 2 times 5. 30 is 2 times 3 times 5. And finally, 60 is 2 times 2 times 3 times 5. So, what do all of these have in common? Each divisor uses only the prime factors that already appear in the prime factorization of 60. These only involve 2s, 3s, and 5s. In other words, every divisor of 60 is made up from the same selection of primes, a 2, a second 2, a 3, and a 5, using no extra primes and not using any prime number more times than 60 does. This is a huge idea. Each of these rows has exactly 2 2s in it, it has exactly 1 3, and it has exactly 1 5. Next, I want to find the prime factorization of 420. This is 42 times 10. 42 is 6 times 7. And 10 is 2 times 5. 6 is 2 times 3. So at the end of this one, I have 2 times 2, times 3, times 5, times 7. Next, what about 4620? This is 462 times 10. And 462 is the same thing as 6 times 77. 6 is 2 times 3. 77 is 7 times 11. And 10 is 2 times 5. So for this one, we have 2 times 2 times 3 times 5 times 7 times 11. Now, I want to test for divisibility. So this first number here, this was 420. And this is 4,620. First, I want to know, is 420 divisible by 66? The prime factorization of 66 is 2 times 3 times 11. But I can see that I'm missing this 11 in 420. I have a 2 and a 3, but there's no 11 in the prime factorization of 420. So 420 is not divisible by 66. Is 420 divisible by 56? Well, 56 is 2 times 2 times 2 times 7. But 420 only has 2 2's, not 3. So 420 is not divisible by 56. What about 70? This one is 2 times 5 times 7. And all of those prime factorizations are contained in 420. 420 does have a 2, a 5, and a 7. So 420 is divisible by 70. What about the number that breaks up into 2 times 3 times 5 times 5 times 7? Well, this product contains 2 5's, and 420 only has 1 5. So 420 is not divisible by that number. What about 4,620? For 66, we had 2 times 3 times 11. And in this, we do have a 2, a 3, and 11. So yes, 4,620 is divisible by 66. For 56, we had 2 times 2 times 2 times 7. But 4,620 only has 2 2's, not 3. So no. For 70, 2 times 5 times 7, I do have all of those factors, so yes. And then this final one, 4,620, only has 1 5, not 2. So no, it is not divisible by this number. This is such an efficient way to reason about divisibility. We do not have to divide every time. We can compare prime factorizations. Now, let's connect prime factorizations to factor pairs. We know that 108 is 2 times 2 times 3 times 3 times 3. So when I'm finding a factor pair, if one is 2, the other factor must be the product of the remaining primes. 2 times 3 times 3 times 3, which is 54. So one factor pair would be 2 and 54. Let's use this idea to find all the factor pairs of 108. I've already pulled kind of a 2 off to the side. What if I have a 3? Well, that would be 2 times 2 times 3 times 3, which is 36. So that's a second factor pair, 3 and 36. If I remove 2 2's from this, I would have 3 3's left. That would be 4 and 27. So that's a third factor pair. If I pulled off a 2 and a 3 out of this prime factorization, I would have a 2, a 3, and a 3 left. This would be 6 and 18. A 3 and a 3 would give me 9, and I would be left with a 2, and a 3, which is 12. We do always have the factor pair 1 and 108, and that's all of them. I kind of slowly pulled off one of each of my numbers, then I did all the possible combinations of 2 numbers in my prime factorization. And then I didn't have to worry about the groups of 3 numbers because they're already here as a factor pair. Each factor pair comes from splitting the prime factors into 2 groups. Now, let's find all factor pairs of 2 times 5 times 5 times 7 without multiplying first. We can still think structurally. The number has prime factors of 2, 5, 5, and 7. So my possible pairs, we would always have 1 and the given number, 2 times 5 times 5 times 7. I can pull a 2 out of this prime factorization. When I do, I'm left with a 5 times 5 times 7. I can pull a 5 out of this prime factorization. When I do, I'm left with 2 times 5 times 7. I could pull a 7 out of the factorization. Then I'm left with 2 times 5 times 5. That's all the ways I can pull one number out, so let's look at pulling 2 numbers out, a 2 and a 5. If I did that, I'd be left with a 5 and a 7. I could also do a 2 and a 7. If I did that, I'd be left with a 5 and a 5. And that's actually it, because all of the other possible combinations of 2 would be 5 and 5, which I already have, and 5 and 7, which we already have. If we choose to evaluate them, these become 1 in 350, 2 in 175, 5 in 70, 7 in 50, 10 in 35, and 14 in 25. This is a powerful way to reason before computing. As future teachers, that matters. We want students to see structure, not just push numbers around. You've just worked through a lot of rich mathematics, and that is something to feel good about. The goal is not speed. The goal is understanding. When you teach this to children, visual models, repeated language, and careful comparisons will make a big difference. And the more clearly you understand the structure now, the more confidently you will be able to support your students later. Excellent work.